Hello, welcome back. The title of this lesson is called Calculating with Significant Figures, and this is part 1. So in the last lesson, we learned how to look at a number and determine which digits are what we call significant. In other words, those are the digits that we're sure about. Because every time you measure something in real life, like I'm not talking about counting rocks or counting eggs. I mean, those are called exact situations where you're always going to get the same answer every single time. Or if a conversion factor is given to you as fact, like 12 dozen of something equals 12, or 1 dozen of something equals 12 eggs. Those are exact numbers. But in the real world, most things aren't exact. We're measuring things. And if you do repeated measurements over and over and over again, you'll notice the last digit on the display, or if you're reading an analog gauge, it's very difficult to figure out what the last digit is because you're kind of interpolating or kind of guessing, and based on your experience, what that last digit is. So there's always some uncertainty in the trailing digits of a number. So the numbers that we're sure about, the ones that we're sure are correct, are called significant. And then, of course, there are the non-significant, or the other digits there that we're not really sure about. So in the last lesson, we learned how to count these significant digits, and now we're going to learn how to calculate with them. So there's 2 main rules we have to learn. They're very easy, but it does take some practice to get the hang of it and remember it. We have a rule that we use when we add or subtract numbers, and we have a rule that we use when we multiply or divide numbers. And that's going to cover the vast majority of everything you're going to do in chemistry. Especially in chemistry, we're mostly multiplying or dividing things. So instead of writing a large definition on the board, I'm going to show you with examples what we do in these different situations. So let's talk about the case when we're adding and subtracting. Right? Now we know from math that the addition of 2 numbers and the subtraction of 2 numbers are really the same thing, because anytime you subtract something, you can say that it's the same thing as adding a negative number. So the operation we call subtraction is really the addition of negative numbers, and so that's why adding and subtracting are lumped together. Same thing with multiplication and division. They're closely related like that, and that's why we're grouping them like this. So let's take the very simple problem. And it's going to be 20.42. This could be number of grams of something or whatever it is. It doesn't matter. And this is going to be 1.322. And then we're going to add to that 83.1. Now notice that these numbers have a different number of digits after the decimal point. This one only has something in the tenths place. This number has hundredths place. And this number has a thousandths place. So what it means when you have a number that has more digits after the decimal point, it just means you're more sure of the truth, of the accuracy of that number. The more digits you put, the more sure you are of the truthfulness of that number. The fewer digits you have, the more uncertain you are about its actual value. That's what digits do for us. They give us a feeling for how sure we are that the number we have measured is actually the real value of what it is we're trying to do. So when you look at this, as far as the decimals go, we're a little more sure of this number than maybe some of these other ones right here. All right, now what we do when we just add these up straight in a calculator and retain all of the numbers, all of the decimals and everything, just add it up, we get 104.842. All right, now what are we going to do when we actually add these guys up? We get this number here. Now, the question is, should we retain all of these digits or not? So the answer we get is 3 digits after the decimal. The rule for addition and subtraction is that you're going to round this number, and what we're going to round it to is going to be 104.8. This is the number we're going to say is the correct value. And the reason is because this number has 2 digits after the decimal. This number has 3 digits after the decimal. This number has 1 digit after the decimal. So because there's 1 digit after the decimal, we only want 1 digit after the decimal in our answer. So I could write a large definition and say, when adding or subtracting numbers with significant figures, make sure your answer has the number of digits after its decimal point as the least number of digits after the decimal point in your problem statement. That's just a really long-winded way of saying, hey, when you're adding or subtracting, you don't count significant figures. You're not counting the significant figures. All you're doing is you're looking at how many digits after the decimal. How many digits after the decimal here? How many digits after the decimal here? And then what we're doing is we're just going to say, okay, which one's the limiting factor? This one only has one digit after the decimal, so my answer is going to only have one digit after the decimal. So all you're doing is looking at how many places after the decimal I have in the numbers I'm adding or subtracting. Whichever one is the smallest one is like the limiting factor. That's the one I'm least sure of. And so my answer, I'm just going to put the same number of digits after the decimal. And that's how you handle addition and subtraction. All right. Now we're going to do a lot more problems. Don't stress out about that. I'm just trying to get the rules on the board. Let's talk about multiplication and division. What do we do for multiplication and division? It's a little bit of a different rule. And that's because the operation of addition and subtraction is a little bit different than multiplying and dividing. Let's say I have 6.221, and here I have multiplied it by 5.2, so I'm multiplying here. Now, if you just take this number in a calculator and take this number in a calculator or do it by hand and multiply it out, the full number you get is 32.3492. But do we keep all of these decimals or not? And the rule is different from addition and subtraction. For multiplication and divisions, here is what you do. You look in the numbers that you're operating with and you count significant digits. 1, 2, 3, 4 significant figures. And here you have 2 significant figures. If you're not sure how to count significant figures, then you need to go back to the last lesson. We already learned that skill. In this case, all of these digits are significant, and all of these digits are also significant. So you have 4 and you have 2. And what you do is you say, which one's the limiting factor? This number only has 2 significant figures. I'm basically less sure about this number. So this I'm going to apply to my answer. And I'm going to say that my answer then can only have 2 significant figures. But the first 2 digits are before the decimal point. So what I'm basically saying, I have to round it to this position, 2 significant figures. The 3 is the next digit over is less than 5. So I basically round it to 32. And that's what I'm going to round it to 2 significant figures, and it's going to be 32. Now this kind of thing looks weird to students because when you multiply decimals, you kind of expect to see a decimal in your answer. And here we've basically thrown away all the information after the decimal point. You're like, well, how is that the case? And the reason is because whatever I'm multiplying here, I'm extremely confident in the truthfulness of this number because I have a lot of digits. But here, I'm just not as comfortable with this. I'm less sure of this one. And so when you multiply it, you have to make sure that your answer reflects the level of certainty that you have as compared to the numbers you started with, because it's like garbage in, garbage out, right? If you have a lot of garbage data coming in that you're not sure about, then you can't carry all of these significant digits in your answer. There's 1, 2, 3, 4, 5, 6, because this would imply that you're extremely sure that the answer is close to reality. All those digits, that's what it implies. But in your initial input data, you're not sure of this one at all. So why would you claim truthfulness or accuracy in your answer when you have garbage coming in? If you have garbage data coming in, you get garbage data out. So even though it looks a little weird to throw away this information, you're really only sure of this answer to 2 significant figures because of the data coming in. So there's 2 rules, and we are going to do a lot of problems, so don't stress about that. But here are the 2 rules. If you're multiplying or dividing, you are actually counting significant figures. You're not necessarily worried about decimal positions. You're just counting the total significant figures. Whichever number has the fewest significant figures in your problem, that's how many significant figures you round it to in your answer. And if you're separately adding or subtracting numbers, then you're not counting significant figures, you're simply counting digits after the decimal point. And whatever is number there that has the smallest amount of digits after the decimal point dictates how many digits after the answer that you have. Notice we didn't count significant figures in the addition and subtraction. We're only looking at what's after the decimal point for adding and subtracting. Now, the tricky part of the situation comes with the following. There's a couple little things I do need to talk to you about. Some numbers are what we call exact numbers, and we talked about that in the last lesson. 12 dozen eggs, or 12 eggs is equal to 1 dozen. The number 12 there, you would think the number 12, like if I just have a problem here, let's say, and I talk about, 12 eggs is equal to 1 dozen. Right? Or if we're doing some calculation and we use the conversion factor that 1,000 meters is equal to 1 kilometer. How many significant figures here are in 1 kilometer? Well, it's only a number 1. You would think there's only one significant figure. So if I do a calculation where I convert between kilometers and meters, and I have that 1 sitting there, then you might be tempted to only make your answer 1 significant figure. Because remember, what you're doing when you multiply or divide is you're looking at whichever number has the least significant figures, and then you're applying that to your answer and rounding. But if I multiply by 1 kilometer, then I might round my answer to one place, because 1 significant figure, because the number 1 is only 1 significant figure. So that's clearly ridiculous. You shouldn't do that. And the reason is that because situations like this involving conversion factors are what we call exact numbers. It is defined that 1 kilometer is equal to 1,000 meters. It is defined that 1 dozen eggs is equal to 12. If I have 6 rocks or 5 balloons, those are exact numbers. You're not going to miscount the number of balloons, okay? When we talk about significant figures, we're mostly talking about measured quantities, the number of grams of something, right? Or the volume of something is not always exactly able to be known either, right? Things like that. So basically, the bottom line is if you see exact numbers in your calculation, like a conversion factor, you don't look at the significant figures at all. You assume that they have infinity accuracy. So they have infinite number of significant figures. Even though the number is only number 1, you basically don't consider it as far as significant figures because it's an exact number. And the second thing I need to talk to you about is, here we've talked about adding and subtracting, and here we've talked about multiplying and dividing. Fairly easy. What happens if you have a long calculation where you add some numbers together, then you take the result, you multiply by something else, take that result, add it to something else, take that result and multiply by something else or divide it or whatever. When you have a chained calculation like that, where the result of one thing goes into something else, the result of that goes into something else, the result of that goes into something else, there's a little bit of a risk. Because if you start rounding every step of the way, like if you do an addition first and then you round the answer, take that answer and stick it into the next part, which is multiplication, and then round the answer again. And then take that and put it somewhere else and round it again. If you intermediately round all the time, you're going to introduce errors in your calculation that are going to get bigger and bigger and bigger the more you do that. So even though these are the rules, what we typically do is we don't really round until we get all the way to the final answer. You usually keep extra digits in your calculation and just kind of flow one into the other, but then at the very end is when you apply your ideas here of significant figures and you round it at the end. So we have rules for adding and subtracting. We have rules for multiplying and dividing. And then we are told that we have exact numbers. You kind of ignore those when it comes to significant figures. And then we also, if we have chained calculations, you kind of keep your digits, kind of like don't round anything till you get to the end, then you round the number. And you have to do some thinking there a little bit. So what we're going to do now is a bunch of problems to practice these skills. All right, so let's tackle problem number 1. Right, problem number 1. Let's tackle the following problem. What about 14.35050, and we're going to add to that 2.650. So what we're going to do is add these up, and then we're going to figure out where to round it. So if you just take this in a calculator and add it to this number, or you can do it by hand if you really want to inflict some pain on yourself, what you're going to get is 17.0005. All right, and now we have to ask ourselves, is this the right number of digits or not? Now this is addition going on. So for addition, what we do is we only consider the decimals. We don't consider significant figures of the whole number. We only look, there's 1, 2, 3, 4, 5 decimal numbers after the decimal point. Here, there's 1, 2, 3 numbers after the decimal point. So since there are 3 digits after this decimal point and 1, 2, 3, 4, 5 here, this is the limiting factor, and my answer should only have 3 digits after the decimal point here. So 17 point, we have to round to this position here. Now next door is a 5. Anything 5 or greater means I round up, so 001 would be the final answer, 17.001. All right, let's take a look at B. What if I have 952.70 minus 140.73890? All right, well, when I add these numbers, or when I subtract these numbers, this minus this, what do I actually get? I get 811.96 or 9611. And how do I determine what decimal to round to? Well, this number, since it's a subtraction, I'm only looking at 2 digits after the decimal. This one has 1, 2, 3, 4, 5 after the decimal. The limiting factor, the smaller one, is 2 digits after the decimal. So I must round this number to the second decimal point. That would be the 6 here. So basically, it's going to be 811.96 because the next door number over is a 1, which is less than 5. So, of course, I just round it down to 811.96. So you see, in both of these problems, I'm not counting significant figures in all the numbers in the problem. I'm just looking at the number of digits after the decimal point. All right, let's take a look at part C here. What about the problem 3.290 times 10 to the 4th power? Now multiply that by 0.25010. Now, this is a multiplication problem. So I don't do what I was doing a minute ago. I don't just look at the decimals. I have to go down and actually count the significant figures of the numbers that are in my problem statement. Before we do that, let's go ahead and just actually multiply this. If we take this number times 10 to the 4th and we multiply times this number, what we actually get is 8228.29. Now, how many significant figures do we round to? In this number, remember, for the scientific notation, we don't count the 10 to the whatever as significant. That doesn't count at all. So the number of significant figures is 1, 2, 3, 4. This 0 counts as significant because it is a trailing 0 after a decimal. So there's 4 significant figures here. In this number, leading zeros don't count, so we have 1, 2, 3, 4, 5. All of these are significant. This is a 0 that's sandwiched, and this one is a trailing 0 after a decimal. So 5 significant figures, 4 significant figures, so I need to round this one to its 4th significant figure, which is the 8. So actually, it's going to be 8228 because the next door number is a 2, which means I round down to the 8, and so 8228. Now, I can write that in scientific notation if I want as 8.228 times 10 to the 3, if I want to. I don't have to. That's still 4 significant figures, and you move the decimal 1, 2, 3, which has given me exactly the same answer. Now, I can choose to do that or not, as far as the scientific notation part of it. All right? Part D, let's take a look at 0.05880, and we're going to divide that by 0.6770. So first, if we actually take the top number and divide by the bottom number, we actually, in a calculator, get 0.08685 and 4. Now, how do we round it? In the top number, we have 1, 2, 3, 4 significant figures. This one doesn't count because it's not sandwiched and it's not a trailing 0. And this one doesn't count. Basically, they're both leading zeros, so we ignore both of those. So we have 4 digits in the top, and we also have 4 digits in the bottom. This one's trailing, so it counts, and this one's leading, so it doesn't. 4 significant figures, 4 significant figures. Of course, they're the same, so I'm going to round it to 4 significant figures. This number is not significant. This number is not significant. They're both leading zeros. So this is 1, 2, 3, 4. That's the 4th significant figure. And this one is less than 5, so I'm going to round down. So it's going to be 0.086 and a 5. Let's see here, 86. Whoops, I forgot the number 8 here. 8685. Basically, I round down here 0.8685, and that's the final answer to 4 significant figures. All right, we're making good progress. Let's continue on with a few more just to wrap up our skills. All right, so here we have problem number 2. This problem is a little bit tougher because we have more numbers involved, but it's the same idea. So let's say we have problem number 2A. We're going to add the following numbers: 212.20. We're going to add to that 26.70, and we're going to add to that 402.090. So the first thing to do is just dump this into a calculator and get the number that you get. So when you add all of these up, 212.20, 26.70, 402.090, you get 640.99. All right, so that's what we get. So let's see what we actually get as far as significant figures. So this is addition. They're all addition, right? So we only look at after the decimal. There's 2 significant figures here, 2 significant figures here, and there's actually 3 significant figures here. Because this is a trailing 0 after a decimal, it counts. This 0 is sandwiched between 2 non-zero digits, so that counts. So we have 3 digits after the decimal point, but these each have 2 digits after the decimal point. That means our answer has to have only 2 digits because this is smaller than the 3 digits, and our answer already does have 2 digits, so we don't actually round anything. The answer is 640.99. All right, let's take a look at B. B is 1.00280. We're going to add to that 0.2210. And we're going to add to that 0.10337. Now, when we add all of these numbers up, we get 1.32717. And then we have to ask ourselves, how many significant figures do we round to? Well, there's 1, 2, 3, 4, 5 after the decimal. There's 1, 2, 3, 4 after the decimal. There's 1, 2, 3, 4, 5 after the decimal. So the smallest of all these numbers is the 4 after this decimal. So we have to have 4 digits after the decimal in our answer, which means we're going to round to this position. And this one must turn into a 2 because the next door number is larger than 5. 5 or larger. So 1.3272. This turns into a 2 because the 7 forces it. 1.3272, that's the final answer. All right. What about 52.3310? And we're going to add to that 26.010. And then we're going to subtract from that 0.99810. So when you dump this into a calculator and you add these and then you subtract this, you're going to get 77.3429. And then we ask ourselves, how do we round this? Well, this number has, since it's only addition and subtraction going on, we look at the decimals. 4 digits after the decimal, 3 digits after the decimal, and this is 5 digits after the decimal. The smaller of those, the limiting factor, is the 3 digits after this decimal. So I must have only 3 digits after my answer here. I'm going to round to this position, which will make it 77.343. This goes to a 3 because the next door neighbor is larger than or equal to 5. So 77.343. All right, we only have 2 more little problems like this. 2 more little calculations, and we're done. And these are going to involve multiplication and division. So this is part D. We're going to have 2.010 times 10 to the power of 2. I misspoke earlier. This one's going to involve addition and subtraction as well. So we have 3.0140 times 10 to the power of 3. We have to be careful with this situation because we have scientific notation here. It's very easy to say, well, I'll just count these as 3 digits after the decimal and 4 digits after the decimal, so my answer has to have 3 digits after the decimal. But because the scientific notation forces you to write it with a bunch of digits after the decimal, when you're adding and subtracting, it's kind of hard at a glance to know what to do. When you have scientific notation like this, it's going to be actually perfectly legal about it, then what you really should do is turn this into a decimal, first of all. The decimal goes 2 spots to the right, 201.0. That's what this is right here. And then we're going to add this one. Here, the decimal goes 1, 2, 3 to the right, 3014.0. So now it's much clearer what's going on. There's only 1 digit after both of these numbers, so the answer is only going to have 1 digit after the decimal. If you looked at the original problem, you would think that there would be a lot more digits after the decimal. So if you're adding numbers with large scientific notations, it's better to convert them to a decimal to see how many decimal points you need. So now that we have it into this form here, we can just add these numbers together and we're going to get 3215.0. And we need 1 digit after the decimal in our answer because each of the numbers we started with did as well. So this is already rounded. We don't have to do anything. 3215.0. All right, next problem. We're going to have 7.2550 minus 6.834 6.83500. So when you take this number and you subtract this number, what you get is 0.42. That's what you would get in a decimal, in a calculator, in terms of a decimal. But we see that we have 4 digits after this decimal, and because we're subtracting, we're only looking after the decimal, and we have 5 digits here. So our answer has to have 4 digits, but we only have 2 digits in our answer. So what we have to do is pad the answer with 2 extra zeros. To make it have 4 digits after the decimal that are significant, we add 2 zeros, which you can add trailing zeros as many as you want, and it doesn't change the value of the number. So we get 0.4200 as the final answer. All right, we have just a couple more really quick ones involving multiplication and division. Let's look at 17.2. I'm going to multiply that by 13.3430. So if you run this through a calculator, the number that you're going to get is 229.4996. Now, since it's multiplying and dividing, we need to count significant figures. There's 3 significant figures total here, and there's 1, 2, 3, 4, 5, 6 here. The limiting factor is the 3 significant figures, so my answer must have 3 significant figures. So I'm going to round it to this position. So it stays at 229, and this is the final answer. The 4 is less than 5, so I don't go up here. 229 is the answer. And for our very last problem, what if you have 1.347 times 10 to the power of 2, and you divide that by 6.0002 times 10 to the power of 2? So here we have the scientific notation, of course. If you put these numbers in a calculator and divide it, you're going to get a very long decimal, 0.224492517, and actually the decimals keep going. So I just kind of stopped it right there. Now, in my original problem statement, we have 4 significant figures here. We don't look at the exponent at all. That doesn't apply. Only 4. And here we have 1, 2, 3, 4, 5. All of these zeros are significant because they're sandwiched. So we have 5 here and 4 here. That means the smaller number is 4. I must have 4 digits in my answer of significance. So that means I round to here. So 0.224, and this becomes a 5 because this kicks it over and makes it a 5. So 0.2245. So in this lesson, we've covered a lot. We talked about that we know how to count significant figures, and then we showed the rules for adding and subtracting, and also which only involve the decimal, the numbers after the decimal, and then we shared the rules for multiplying and dividing. And we practiced them. Now in chemistry, most of the time you're going to be multiplying and dividing. I mean, you add as well, but a lot of the problems are multiplication and division, so that's what we're going to be probably end up using a little more. But we still need to know all the rules, of course. So I'd like you to solve all of these. Follow me up to part 2. We'll do a little bit more calculations with significant figures that are a touch more complicated with chained calculations one after another. So follow me on to the next lesson. We'll conquer that and continue to build your skills.